Okay, so hello everyone. Today we're going to talk about evaluating neural networks. And as usual, some logistics. For now, we have the second programming assignment out. And this is going to be an assignment about multi-layer perceptron. And the idea here is to implement the same or a different model for the same problem of classifying images of cats and dogs. It's the same data set as the previous assignment. And I wanted to see that if you use a bigger model, you can get better performance. So at the end, you should see a higher performance than the previous assignment on the same problem by using a large neural network. And the way the code is structured is it's based on functions. So I'm not using classes in this assignment, for those of you familiar with object-oriented programming. And especially for those of you who are used to program in libraries like PyTorch, where you normally write classes to define models, you might find this a little bit weird that we are not using classes. But this is intentional. We're going to move, in the next assignments, we're going to move to work with PyTorch. And then there, we're going to actually have classes for loading the data and classes for designing the model. But here, I'm trying to make it more old-style imperative programming by just calling functions. And the main functions of these assignments are the ones that we actually already did in the previous assignments, which are the functions for loading the data set. But then the new ones here would be the forward model, or the forward pass for the multi-layer perceptron. And perhaps the hardest challenge of this assignment is the backward pass. And I want you to pay attention to this because last lecture, when we talked about backpropagation, we used this idea of a computational graph, which normally is more, I guess, intuitively programmed with this node class that we actually, the same way we actually saw last time. But here, for this assignment, we still have a computational graph, but it's more like an implicit graph. It's going to be there, and if you look at the slides and look at the code, you should be able to see that, in fact, there is a graph in there when you do the backpropagation backwards from the last layer, or from the loss function all the way to the first layer. So it is there, it's just not explicitly programmed using this kind of node function or graph, node class or value class as we saw last lecture. Anyways, I'll give you time to work with this, and if you get confused, or if the assignment, or if the way the code is organized is not making sense for you, then let me know or ask others on the chat. Okay? So we already, I already kind of like reviewed what we talked last time, which was mainly the idea of the backpropagation algorithm. That is this algorithm for computing the gradients of a neural network, and it uses this idea of a computational graph. And we saw how to compute the gradients for logistic regression and the multi-layer perceptron using this idea. Any questions or comments before we get started? All right, so for today, we're going to talk about evaluating models. I think now it's a good time. We always have to have this kind of lecture. Most of our lectures are going to be algorithms and models, but at some point we need to stop and actually discuss how to evaluate them. And this is going to be our lecture for that. We've seen a couple of models so far: logistic regression, linear regression, the perceptron, and multi-layer perceptron. So we know 4 different algorithms, 3 for classification and 1 for regression. Actually 2 for regression, because neural networks can work both for classification and regression. So now it's a good time to ask okay, how do I select a model? How do I evaluate models, and how do I pick a model for a given problem? And to talk about that, I want to discuss how to split our data set into training, validation, and testing. Then I'm going to discuss some metrics to evaluate regression models and classification models. Particularly for classification, we're going to discuss the confusion matrix, which is this matrix for computing most of the classification metrics we use, which are accuracy, precision, recall, and F1 score. Okay. I guess that's it. So let's get started. So just a quick reminder that we've seen this generic algorithm called multi-layer perceptron that we can configure to have as many hidden layers as we want. And it can have as many hidden units or hidden neurons as we want, right? And so because of this generality, we normally, especially nowadays, we don't use the name multi-layer perceptron anymore. It's still a valid name. If you say that name, people will understand it, and you won't be wrong. But right now, it's more commonly, the term fully connected neural network is more common. Mainly because, I guess, multi-layer perceptron is not actually made out of perceptrons, right? Because the perceptron itself has a threshold activation function that is not differentiable. So in fact, we can't use the perceptron to build MLPs. Instead, we use these sigmoid neurons or ReLU neurons more commonly these days. So because of that, it's kind of like a misleading name, especially with the current state of these models. So from now on, when I say fully connected neural network, I'm meaning these multi-layer perceptrons in a general way. Like, I'm not specifying any specific activation function or any specific number of layers or any specific number of hidden units. I'm talking about this general model. And this is the scheme or diagram of a general fully connected neural network. I'm hiding the number of neurons in the input layer and in the output layer because these are defined by the problem. Right? Remember that the number of input units is defined by the number of input features you have. And the number of neurons in the output layer is defined by the number of classes you have in your problem, if it's a multi-class problem. If it's a binary classification problem, then you have only one single neuron. If it's a regression, it's the same. But the question here is that I want to discuss in this lecture is, how do we choose these hyperparameters, A, B, and C? In other words, number of layers, number of hidden units, and activation functions. Okay. So recall that we have structured our machine learning cycle or workflow, if you will, in 3 steps. Right? We first acquire experiences, and then we train a model, and now I'm actually specializing this diagram for neural networks or for deep learning. And that's the kind of life cycle of a deep learning project. You acquire data, then you get a data set, and here I'm talking about supervised learning. So there is this data set of pairs, X, Y. I have M examples. Then I train a model that can be either a classification or regression model. And here this model is a neural network. That so far we only know how to train these fully connected neural networks, but in the next weeks we're going to see different types of architecture. So at this stage, you have to decide like how my models are going to look like. I have to pick a model, or I have to experiment to pick one model. So I have to decide the number of layers, the number of hidden units, which activation functions to use, and several other hyperparameters of these models. But then at the end, I learn a function, edge of x, and I evaluate this model on unseen examples. Okay? So this is still the same framework. And I can keep doing this until I'm satisfied with the model itself, or I'm satisfied with the performance, or I run out of time if you are working in the industry and you have like a budget of time to train a model. Okay. But right now, I want to talk a little bit about the data set itself. So recall as well that we've already discussed this idea that in machine learning, we want to evaluate the performance of our models in unseen examples. And to do that, we normally split our data set into three disjoint subsets that we call training set, validation set, and test set. And we use these three splits to evaluate our model. And these sets, or splits, they have different purposes. Right? The training set we use to actually train the model. And then the validation set we use to select the best model. So the way you can think here is, you can think of this life cycle of, I have my training set, and I train my model, and I get an error or a performance metric. And then I run this, I evaluate the same model, trained on the training set, on the validation set. And I'm going to get a validation error or performance. Right? And I can keep tweaking this model until I get low error in the validation set. So I can stay in a loop here of training and validation until I get a very low or a satisfiable validation error, something that is good for me. Once I'm satisfied with this validation error, then I report my final performance on this test set. So so that's also why the validation set sometimes is called development set, because it's the set used to develop your model. So you're always trying to optimize for this validation error. And next lecture, we're going to talk about techniques to use in both of these steps. So for instance, if you are in the training step and you still get very high error on this training set, we call this underfitting. And then in neural networks, it's a little bit easy how to solve this problem, because you can always increase the number of layers, increase the number of hidden units. You're going to make your model bigger, and eventually it's going to fit your data or your training data. Okay? That doesn't mean that fitting your training data well is going to give you a good fit on the validation set, because you might actually overfit to the training data. So then you have to come back and now, okay, maybe you have to reduce your model a little bit, and then you have to play this game of increasing and reducing your model, or using some other techniques for dealing with overfitting until you are satisfied. And once you're done, then you just use the test set to report your final error. Okay? So you can think of this loop here between training and validation as kind of like increasing and decreasing your model to get a good balance between training error and validation error. Okay? Yes?
How much from the data set we set for each step of this?
It seems that you actually have seen this slide before, because that's exactly what I'm going to talk right now. So to answer your question, here are some ideas of how to split, or how much you should split your data set for training, validation, and test. So imagine that this bar there is your full data set, and then you have these splits, training, validation, and testing. As you can see here, normally we have more training data, and then we have a little less validation data, and even maybe less or the same amount between validation and testing. Okay? And in traditional machine learning, or back in the day, when we had low data regimes, and here I'm picking a number that is an example and makes sense, like if you have about, let's say, 1,000 examples or less, or a little bit more than that, even maybe up to 10,000 examples. In these low data regimes, the most common split would be 60-20-20 if you had training, validation, and testing. Or if you didn't want a validation test, you would split into just training and testing, and that would be 70-30%. Okay, so if you have 100 data points, you would use 70 of them for training and 30 for testing. Or 60 for training, 20 for validation, and 20 for testing. Okay? So in modern deep learning, the number is a little bit different because now we are talking about this big data regime where we have maybe millions of data points. And now these percentages, they start to, at least for validation and testing, they start to get lower. And you get higher percentages for training. Because if you had, let's say, 1 million examples in your data set, right? If you pick 5% of this, how much is that? 50,000. Right? So that's actually already a lot of data for testing. Right? So you would have splits like this: 95 training and 5% testing, or 98-1-1. Okay? Because in fact the data set is so large that even 1% is already a lot. Okay? Question? No? So, as you probably imagined, or you might be wondering, why is it possible, or how is it possible to not have a validation set? Well, it's common, especially when you don't have enough data, or if you don't actually need what we call an unbiased estimator of your error. Right? If you don't actually worry too much about that, then you might just have training and testing. Okay. And this might be the case in practical applications. So be aware that it's normal and it's okay to have that. And in this case, your test set is your validation set, which means you're going to develop your model in your test set, and you might be actually biasing your model towards that set. But if you are in this big data set regime, your data set itself, your test set might be large enough that biasing towards that data set won't be a big problem because you already have a lot of data in there. So you already have a good representation of a large space of examples. And something that is extremely important is that these subsets have to be disjoint, or you can't have any examples that are in your training set in your validation or test set. Right? Because the whole idea here is to measure generalization. Right? If I have a copy, if I have examples that I've seen before in the training set, exactly copied in the validation and testing, then I'm not measuring generalization. because my model might be actually memorizing these examples, and then measuring accuracy on those examples is the same of just measuring how good my model is in memorizing those, right? So when you're building a data set, you have to be extremely careful that you don't have these duplicates, right? And this might not be actually as easy as you think. Because let's say if you're working with textual data, maybe each of your data points is an email, right? So then you have to make sure, oh, this email doesn't appear twice in my data set, exactly this email. But there might exist another email that is very similar to that. And sometimes even very similar examples you might need to remove. But that's very case dependent, okay? Same for images, right? It's very rare to have two exact same images, but you might have very, very similar images, two images that are extremely similar, right? They're same angle, maybe just changes the time of the day or something. Same person, same frame, same everything, except it's like 1 hour later than the previous one. So the content of the image is exactly the same, you just have a slightly different distribution of pixels. So in that case, you should have to think about what to do. It depends on what you're trying to achieve, okay? Question? So we've talked about how much to put into training, validation, and testing, but I didn't talk about how to actually split the data. Right? And you have to be very careful about that. And this is actually this problem that we talked on the board is an example that you have to look at your data and understand what you want and what you need essentially to measure. And then you have to split your data to simulate what is going to happen in the real world. Okay? And all of this is very generic. Let me give you an example. So the most standard approach for splitting your data is splitting uniformly at random. So look at this data set here. Red means training, purple means validation, and blue means testing. Here we have 10 data points, right? And I'm using 6 for training, 2 for validation, 2 for testing, and I chose them uniformly at random. Okay? So this is the most common way, and this is especially used when you have this when you have this data that is IID or independently. Identically and independently distributed, sorry. Don't worry too much about that, but that means that a given sample on your data set doesn't depend on any other previous sample, okay? They were sampled independently, like images. If you took one picture today, this has nothing to do with a picture we took maybe 3 days ago, or those are two completely independent samples, right? So in this case, you might just uniformly sample or split your data. But if your data has a temporal component, let's say in spam filtering, right? You have to split your data in time. Okay? So now here, consider that your data set, or this now spam filtering data set, has still 10 data points. But the first 6 examples now are used for training, and the next 2 for validation, and the last 2 for testing. Because think about what's going to happen in real life, right? You're going to receive a bunch of emails over time. Let's say you're going to collect data over like a span of 3 months. Then you train your data. Then you train your model, sorry. Then you pick more emails, and then you classify them by hand maybe, and then you evaluate your model. Because that's how your model is going to work in real life. Right? You're going to predict the future. You can't have emails from the future to train your model. Because you might have, for example, if you have a spammer that you're trying to catch, right, might have a specific style of writing these spam emails. So if you have seen one of them, then your problem becomes much easier because you know now that this email is going to come in the future. But if you don't know that yet, you're going to have to be able to generalize your model to catch these spammers, maybe from other spammers that you already know. So make sure when you're dealing with temporal components, same for if you are doing weather forecasting, right? If you want to predict the temperature of the next day, right? If you want to predict the weather for September, you can't look at data points from September. You have to look at data points from January to August, right, to predict September, right? So there are several problems that have this temporal component. And in this case, that's how you should be splitting your training data set. And I'm not saying these are the only ones you can select. But definitely never split alphabetically or by feature values or anything like that, okay? So best guess is at random, and if you have this time component, make sure to respect that. Okay, here's another idea. And this idea is for splitting the data set. And this idea is very useful when you are in a very low data regime, or when you have very few examples. Maybe you're working with medical images that are very expensive to capture, that need special machines, or you are in any domain where it's actually expensive to capture data. You might have 30 data points or something like that. And then in this case, if you split at random, you might not get really good generality or good set of examples in your training, validation, or testing sets. In other words, like these splits, they won't be statistically significant, right? And then there is this idea called cross-validation that we can use to solve that problem. And one of the more general approaches is called k-fold cross-validation. And it consists of first splitting the data set into k equal parts. We call them folds. Okay? And I'm going to have an example so you understand these with actual numbers. And then for each of these folds, you're going to use this fold I as a test set, and all the remaining folds as a training set. And then you're going to train the model using this split, and then you go for the next, you go back to step number 2, and now you have a second fold, and so on and so forth. Which means that you're going to train different models for the same data set. And then you're going to report the average result of these folds as your final result. So let me show you with an example. Here we have 15 data points. It's a very limited data set, right? So the way the k-fold cross-validation works is like this. Consider k equals 3. So I'm going to have 3 folds. So if I'm having 3 folds, the size of my fold is going to be 15 over 3, right, divided by 3, which is 5. So the fold is what you see in blue there. So I'm going to use this fold for testing, or the blue data points for testing, and the red ones for training. Okay. So I train the model, and I calculate my testing error or testing performance. So I move to the next fold and then train the model again and get a testing score. But now, notice how I used different examples for training and a different set for testing. So it's a different experiment. Using the same model, let's say if it's a linear regression model, I'm going to train the linear regression on that first fold, or test on the first fold and train on the remaining examples. And now I'm going to do the same for this fold 2 and for fold 3. And then at the end, I have 3 scores, or 3 performance scores. And then what I report at the end is the average of them. So this is a way for you to run different experiments and evaluate your model in different scenarios. So a very special case of k-fold cross-validation is when k equals to n. So that means that your fold has size 1. Okay. So you're going to have, in this case, we have 15 data points, so we would have 15 scores. And this approach is called leave one out, because we pick one data point for testing and train on the remaining ones. And then move to the next data point and do the same, but now keeping this new one as your testing example. So here's the same idea, but now k is equal to n. So this means I'm going to have 15 folds here. This approach is particularly useful when you have this kind of structure in your data set already. So in my PhD, I worked on this problem that we wanted to generate music for tabletop RPG games. And then we had this data set that was composed of episodes of a game. So we would have, let's say, an episode here, one that was maybe 30 minutes long. This was a video. And then we had episode 2, which was another video. Maybe this was 45 minutes long. And then we had 9 of these. And we treated each video as one data point. So here, because and each episode in the story had it was kind of a self-contained part of the story. So here you would have kind of a beginning, a middle, and an end of this kind of scene. And then here would be another scene or chapter, if you will. And then these would be like different chapters of the story. So they were self-contained in a way. So in this case, it makes a lot of sense to do leave one out cross-validation, because we separated 8 examples for training and then tested on the episode that was left. And then we did it. Now we move to episode 2. This one is going to be used for testing now, and then the others for training. Okay, so the data set itself had this structure for us that kind of like almost asked for this kind of evaluation. Okay, and then it was even easier. So this way it was kind of easy to discuss the results. We said, okay, if you actually split, if you train a model here and then generate music for this episode, you can see like how much from these episodes it generalized for this one. Okay, so it's the same kind of these chapters are part of the same story, but they are different. So, for example, here you would have a battle, but in here it's kind of an introduction of the story. So the players are describing themselves. It's a very kind of boring part of the game, which they're setting up their characters. They're setting up the location. And here is like you have a large battle with dragons and whatnot. So they're very different. And maybe one episode is about like stealing a key from a castle, which is a more like suspenseful type of episode or of chapter. So they're different, and we wanted to know how much we could generalize, right? So it's an example that the data set itself kind of asks for this kind of evaluation. We had only 9 episodes, but each one of them were very long. So it was an interesting way of evaluating. So as data scientists, you're going to have to design your evaluation criteria, and you have to design it in a way that it leads you to interesting evaluations or interesting conclusions or meaningful conclusions for the context you are working on. Okay, any questions? And just to kind of give you an idea of what happens these days, here is a list of famous deep learning data sets and their splits. So ImageNet, we talked about it before. It's this large data set of images of 1,000 classes. And there's many versions of this data set. But the most popular one has 1.4 million images. And I believe this is the one used by AlexNet in the ImageNet competition. And the split there is 93.7. So there's 90% of those 1.4 million for training, 3% for validation, and 7% for testing. Okay? You can do the math later to figure out like exactly the numbers. It's also on the website. Here is a similar one that is much smaller, but it's also images. It's called MNIST, and we've talked about it before as well. It has 70K images of handwritten digits. So here you have 10 classes from 0 to 9. And the way they designed the data set, it only comes as like training and tests sets. You have 85 for training and 15 for testing. Okay. You might see if people applying this data set in papers and actually picking the test, that 15%, and splitting in two and then having actually a validation. Right? So that is totally fine. Okay. So in deep learning research, it's very important to keep these splits consistent because then we can actually use them as benchmarks. So people can actually keep improving over them over time. Because if everyone decides to use a different split, then you can't literally compare them, right? Or compare two different models on the same data set. So it's very important to, once you are actually maybe working on a new problem, to specify that and then give that publicly available to people so people can have exactly the same split you used. Right? Because otherwise it's very hard to compare to your previous model. So for natural language processing, there's this data set called PAN3Bank. And based on my experience, it's less common in NLP to have these specific splits. So actually, even this week, I was looking for a data set, and it was hard to me to find data sets that had this very strong splits of like, oh, we've been using this consistently over a couple of years. But this one had it, like the PAN3Bank it has 46,000 sentences from the Wall Street Journal, and they were labeled according to different labels. And the split there was 85, 7.5, 7.5. Okay. And here is one that is slightly smaller in terms of items, but the items themselves are larger. So the Maestro data set is a data set of music performed on a MIDI piano. It's all classical music. They have the music pieces themselves available both in audio and MIDI formats. And they have this 1,276 classical music pieces. So this is kind of like in the low data regime. And if you think about it, yeah, when it comes to music, it's especially these kind of performances, it's very hard to get large data. We do have a lot of music in the world, but most of it is copyrighted. So you can't actually have access to it, legally at least, right? Same for movies and books. Books are a little bit easier because we've been actually writing books for longer in history of humanity. So there's a bunch of books that are published but don't have copyright anymore. So we can actually learn from them, right? There is, in fact, a data set called the Gutenberg Project, that has lots of these books available. But music is a little bit different. So this data set works with classical music because these pieces are not copyrighted anymore. So they're classical for music from the 18th, 19th century mostly. So anyways, so here you have data sets that are popular, that have been used for research even to this day, and they have different sizes and different splits. Okay. So there's no single way to do this. Okay, it's just like there is this standard of like normally 70, 10, 10, or 85 or 90 for training. Okay. So now talking about imbalanced data sets, and I guess Guilherme brought this question before, which is an important problem. We haven't mentioned this, but when you're collecting data, it's ideal to have the same distribution of classes in your data set. Or what I mean by that is the same number of examples per class. So if you have 2 classes and 100 examples, ideally you should have 50 examples for class 0 and 50 for class 1, or roughly about that amount. If you have that scenario, which is the one on the left-hand side, then we call this data set a balanced data set. And that makes your life much easier in terms of evaluation and training models. If you don't have that, you might run into problems. And sometimes that is not very fixable. Because let's say, if you think about even the spam filtering problem, there's way more, normally, right? There's way more like normal emails than spams. Right? So naturally speaking, right? So maybe there's not much you can do in terms of naturally getting your data, because you have just less examples from one class than the other. Same for if you are trying to do fraud prediction in credit cards, right? If the banks do that. When any transaction you do on a credit card, the bank checks for fraud, and automatically, and if it predicts that it's not a fraud, then it's going to just do the transaction normally. But if it thinks it's a fraud, it's going to probably block your card and send you a message saying, okay, this transaction doesn't look right. Make sure, press OK to make sure it's you or something. Right? There's way less frauds in credit cards than actually normal transactions. You have millions or even billions of transactions happening every day. I don't know, but it's a lot, right? But frauds, you have way less. So in these cases, if that's your situation, maybe you're going to have to frame your problem a little differently. So in fact, we have this type of problem called anomaly detection, that is framed differently than supervised learning. Because we can't just make sure our data set is balanced or even close to that. So then we have to solve the problem in a different way, because it doesn't fit into this category very well. But well, we might say that your data set is mildly unbalanced, like the one in the middle, which is normally okay. You might get some problems, but maybe not. Maybe your model will be able to handle that situation. When you get this extremely unbalanced data set, then you might have issues. And there are 2 major issues here that I want to point out, which is the one that Guilherme mentioned, which is when you're splitting your data, if you have way more examples from one class than the other, you might end up having all your 0 examples in the training set and all your 1s examples in the test set, or vice versa, or something like that, right? And then you are not actually solving the problem. It's like in other words, you actually, in consequence, you're going to get the second problem, which is you're going to overfit to the majority class. You might get 99% accuracy on the majority class, but you made, if you look at the predictions, they only predict the majority class. They never, your model never predicts the minority class. So your model is useless. If you're trying to predict fraud, what you want is to predict fraud, and then you can never predict fraud. You can only predict good transactions. That doesn't make, it's not useful at all, right? So it is important to balance your data set if you can. If you can't, then you have to maybe reframe your problem. But here are some approaches to balance a data set. So the first one is oversampling, which is increase the number of examples of your minority class. And you can do that, there's two common ways. You can do that by sampling examples, resampling examples from your minority class, and just having a lot of repeated examples in your minority class. So you're going to have a lot of duplicates. That's one approach, which might not work depending on the situation. And another one is to actually generate synthetic examples. Okay. Maybe you look at the average points, maybe interpolate some examples and get some new ones there. Okay. Or some other approach like this. Or maybe you have a generator. Like nowadays you have ChatGPT and large language models. Maybe they can help you. Okay, generating synthetic data. Downsampling is another approach, which you don't run in this problem of having duplicates, because now you're actually going to downsample the majority class, and normally we do that by randomly selecting examples from the majority class until you reach the size of the minority class, but then you're going to lose a lot of information, right? So that's the problem you end up having now. You might actually have to decrease your data sets so much that you end up losing the information you wanted to capture. Another approach, which is different than these two considerably, is weighting your classes. So the idea here is to assign weights to each class in your loss function. So the idea is I have, let's say, the positive class and the negative class. Right? So I'm going to create two weights, weight W1 and W0, and I want these weights to be proportional to the amount of examples I have for each class, and I'm denoting them N1 and N2. So N1 is the number of examples of the class 1, and W0 is the N0. Oh, sorry, it should be here N0 and N1, not N1 and N2. But basically what I want is, I want W0 times W1 to be equal to W1 times N1. That is equal to, let me fix this right away. I want W0 and 0 to be equal to W1 and 1. That I want to be equal, these two to be equal to the sum of these two examples divided by 2. So what I want to do is I'm going to solve this equation for W0 and W1. And then I would get this. W1 would be N0 plus N1 divided by 2 N1. And W0 would be equal to N0 plus N1 over 2 times N1. Let's go to the board with an example. Maybe we have N0 equals to 100, and this is our majority class. Actually, let's do it the opposite way.
Both of them are divided by 2 times N1?
No.
The second one is N0.
This should be N1 and N0, yes. So if you had N0 equals to 20 and N1 equals to 100, then in this case, W1 would be equal to 120 over 2 times 100, which is 200. And this is 0.6. Is that right? Okay, 0.6. And W0 would be same things, 120, but now divided by 2 times N0. Oh, it's 40 here, right? Okay, so then it's 3. And now you actually are going to put these weights on your loss function. If this is a binary classification problem, you're going to use a BCE loss, right? So you're going to multiply your majority class W1 here by the prediction of this class and W0 by the other, the prediction of the other class. Okay? And see how you're assigning a much higher weight to the minority class and a much lower weight to the majority class. Okay, so we were talking about data sets. There is way more to talk about this, right? If you're maybe if you are in a data science course or a machine learning course, you can talk more about this, of like, how do you clean your data? How do you pre-process your data? So there's a bunch of like common techniques for dealing with common problems in data sets. And this might actually depend on the type of data you have. If you have categorical data, if you have numerical data, if you have text data, audio, images, all of them have different kind of approaches or common approaches for pre-processing and representing them as vectors. So we don't have time here to dig deeper into each one of them. I just want to give you an idea that it's very important to make sure your data set is well defined, has this meaningful split that helps you get a good estimator of error. But now I want to talk about evaluation metrics. Okay, so far we've been talking about loss functions, which we use to train the models, and they are a measure of error. So the lower the loss, the better. And in supervised learning, these values, they are non-negatives because we're trying to predict labels y. And so if your loss is 0, then we predicted all of them correctly. And in the context of neural networks, it's important that these loss functions are differentiable because you want to train them with gradient descent, and so we have to compute the gradients. But now we don't, when you are actually evaluating the models, we don't necessarily need to report loss values because they might be hard to interpret, right? When you look at a value of, let's say, if you look at binary cross entropy values, that might not be very helpful for you to evaluate what's going on. So we humans don't normally talk in loss. We normally talk about accuracy or other metrics that help us understand what's going on. Okay. So I want to talk about some of these metrics right now. So first, regarding regression models, if you have a regression problem, then yes, you're going to report some sort of error metric. And you don't need to actually use the same metric you use for training. We've seen that the most common loss function for training regression models, or the linear regression model, or even a neural network, is the mean squared error. But you don't need to report your final test error using the same metric. You can train using this loss function, and it's good to train on this loss function because it's differentiable. But maybe you're going to report it in a different metric, which is fine, totally fine. But essentially, when you're measuring regression models, we are measuring what we call the residuals, which are the distance, if you will, or the error between the correct value of a given example, y, and the prediction for that example, y hat. So most of the metrics are based on these residuals, but they use them in a different way. So the mean square error just computes the squared of the residuals, right, and sum them and divide by the number of examples. The mean absolute error computes the absolute residual and then sums and divided by the total number of examples. There's another one called root mean square error, which is the mean square error, but now with the square root of that. And there is another one which is slightly different, which is the R squared metric, which is 1 minus this ratio here. If you look at oh, this is slightly wrong. I'm missing some squares there. So the R squared metric is 1 minus, so on the top here, what you get is the sum of the squared residuals divided by the sum of y, which is the true label, the true value, minus the average. So this y bar here that you see is the average value of the y's, of the labels. Okay. So this is, if you remember, this is, you can think of this as the variance of these data here. So in other words, you're comparing your model, which is the top, against an average model. Think about this, right? This is the average of all these y examples. So it should be something about 400 or something, or 370 here. So this number would be the average of your y's. So imagine that you have this model that predicts always the average value. If you do that, that it would give you this model at the bottom, or this error, it would give you an error, or a sum of these squared errors, and then you compare that sum against your errors, or the errors of your model on the top. I'm going to talk about this in the next slides. So let's just compare the mean squared and absolute error metrics. So when you're reporting the error now, what I mean here is, can you turn on the light, please? So what I mean here is you have your train set, you have your validation set, and then you have your test set. Here for training, and this is a regression problem. In your train step, you would probably use mean squared error for loss function. But here and here, you don't need to report this metric. You can report it if you want, but you can report different metrics. You can report, for example, well, if it's the MSE, then it's going to be exactly the same, right? It's going to be that formula, but few properties of MSE they're sensitive to outliers. Okay, so because they're squaring the error. So if you have an outlier that is a y way above than your average, you're going to get a higher MSE. So if you don't want that property, if you don't want to account for outliers, maybe that's not the best metric to pick, because that metric is going to be higher if you have outliers in your data. Also, this metric is not easy to interpret because you're going to get the squares of the errors. So you normally get very high numbers. They are not in the same units of your Y's or of your labels. Remember, if you're measuring house prices, you might have house prices that are, let's say, 1 million or 2 million, and you're going to square that. So you're going to get these really large numbers that are hard to interpret. And this is something, a property of MSE as a evaluation metric. So normally we use that when we are comparing models when large errors are particularly undesirable. Okay. So the mean absolute error is less sensitive to outliers than MSE. And it's good because it has the same unit as your labels. So the output is going to be also the error in terms of, let's say, price. Not price squared, but actual price. Or if you're trying to predict a temperature, your unit is going to be in Fahrenheit or Celsius, right? Not Celsius squared. So it's easier to interpret mean absolute error than MSE. So here you might actually prefer to report MAE, and here as well. But that depends, because when you care about these large errors, then you might want to use mean square error. But here, when you don't care about them, then you might actually want to use mean absolute error. Both of them are common, but it really depends on your data when to use which. And the root mean square error is a nice balance between the two, because it's still sensitive to outliers. So you care about your outliers. You use this metric, because by taking the square root, then you put your final result in the same unit back to the original units. And so you get this nice interpretability, and also you still account for outliers. So it's an interesting metric as well. Again, it really depends on your context when to use which one of them. And I think when you're working in practice, you'll see that some of these metrics make more sense than others right away. Like when you start thinking about them, when you try them out, you see, okay, this makes more sense in my case. Or it makes it easier for me to explain which model to pick. So the R-squared metric, I made these specific slides just because we haven't talked about it, and it's a considerably different metric. It's very interesting because, as I mentioned, the intuition here is, look at this figure here. We have a bunch of data points, and this red line is a model that we fit to the data, and the green line is just a model that predicts the average, always. So always predicts the same value, which is the average. So you're comparing, what this metric does, it compares the model you fit to this average model. And then what you get at the end is a metric between 0 and 1, that the higher that metric, the better. And what is interesting about this is, because it's this normalized metric, it's scale independent. So it doesn't give you an error, let's say, in temperature or in price. It gives you a score between 0 and 1. And that score measures more formally the proportion of variance that is explained by the model. And what is interesting here is that because it's scale independent, it allows you to compare across different data sets. So you can pick the same model, let's say that it fit in one data set, and test it in 3 different other data sets. And this metric is going to be scale independent. So it's going to be independent of the scales of this data set. So it allows you to do that if you want. Maybe you have, let's say, a model that predicted that you fit in 1 year, and then you have these other years you're going to test in different years and see how well your model fit in different years. Let's say for forecast prediction or something. And then you keep the model, change the data set, and you're going to get these values between 0 and 1 that you can actually compare. Question? Okay, so now let's talk about classification metrics, and this is the last part of the lecture. So when we're working with classification problems, most of the performance metrics we use, they are based on what we call a confusion matrix, which shows to us the number of true positives, false positives, true negatives, and false negatives. I'm going to talk about this with an example. So let's get back to our spam filtering example. Here's a logistic regression model trained to fit a data set of emails that are simply represented by the word count. So I pick an email, I count a number of words in there, that's my input feature, X only, and I try to predict just based on that if that's spam or not. So here's a hypothetical data set. The green data points are not spam, they're zeros. The red data points are spams. And you can't probably see there, but there is some examples at the top, at the bottom that are misclassified. So I have one green data point misclassified here in the bottom, and I have two misclassified emails on the top there. So when you are computing the performance of classification models, we typically rely on this confusion matrix, which is this matrix that has as columns the classes we have, and also in the rows. So both in the columns and the rows, I'm going to have all the classes I have. So here I have only spam and not spam. So I'm going to have first column is spam, second column is not spam, and also the first row is spam and the second row is not spam. And in a binary classification problem, we normally give these special names. We say there is a positive class and a negative class. Which one is which? It depends, right? Here I'm saying that spam is a positive class and not spam is a negative class. Right? You might be working on a model for predicting if, let's say, if an image, if a medical image contains like an image of a cancer or not, right? Maybe like having the cancer is positive and not having the cancer is negative, okay? So what are the values of this matrix? So on the main diagonal here, you would have the true predictions, or in the first cell, you have the true positive, which means the number of spams that were correctly marked as spams. We call these the true positives. So my model predicted seven spams, or there were 7 points in my data set that were spams, that my model predicted them correctly. And the same for the negative examples. Remember, negative is not spam. So the way you can interpret the true negative here is the number of data points that were not spams that were marked by not spams by my model. So those are the true negatives. And likewise, I have the false negatives and false positives. So let's look at the false positives first. The false positive is the number of examples in the data set that were spams. Here, there were spams. So this is the ground truth. The rows is the ground truth, which is the actual label of the examples. And the columns here are my predictions. So the false positive is the number of spams that were marked as not spams. And the false negatives are the number of not spams that were marked as spams. And if you count all of them, this is the number of total examples I have. So here I have 1, 2, 3, 4, there's 2 here, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, that's right. 3, 7, 10, 20. Okay, that's all right. So I have 20 points. These 2 points here that you see, there's a little X in them, are my false positives. They are spams, so they have value 1, but my model predicted them as not spams. And this one here is this single false negative here. It is a not spam, but my model classified it as a spam. Okay. So basically, I am counting, the confusion matrix is showing how my model is making mistakes, right, for each class. So if you look at the diagonal, this is what my model got right. And the second diagonal here is what my model got wrong. Okay. And based on these values, we can compute the 4 most common metrics for evaluating classification models, which are accuracy first. Let's talk about it. So for accuracy, we actually already used it in our first assignment. You already implemented it if you have finished the first programming assignment. Perhaps you did it more intuitively, but accuracy is defined by the confusion matrix as well. And it's just the sum of the main diagonal, of the first diagonal, which is 7 plus 10 in this case, divided by the total number of examples. So it's 17 divided by 20, which gives us a value of 85, or 85%. So we can say this model has 85% accuracy. And here we can read this metric as the proportion of all emails correctly classified, both spam and not spam. So second metric is precision, which is the number of true positives divided by the true positives plus false positives. So it's the number 7 there, that first cell, divided by the sum of the values in the row. So it's 7 over 7 plus 2. So I'm dividing by the sum of the row. And that gives us 77.8 precision. And you can interpret this as following. When the filter or the spam filter marks an email as spam, how often it is corrected? So look at we are talking about the first row. First row is only related to real spams. So in my data set, I have 20 examples. 9 of them, which is the first row, 9 of them are actual spams. So I'm evaluating my model only in that scenario. Okay, so now my total becomes the sum of the row, or the sum of spams. So out of all of them, which are spams, how much did I get right? And this is useful when false positives have high cost. What do I mean by that? Right? If you care more about your spam class in this case, for example, if I'm more interested in predicting spams correctly than distributing them among spam and not spam, then I might use precision. I prefer precision over accuracy. Right? Or maybe your data set is not balanced because accuracy, as we saw, it divides by the total amount of examples. So it's kind of hiding a lot of information in there, because if you have more examples from one class than the other, maybe accuracy is not a good idea. So precision is going to look at it's going to divide your corrected guesses, 7, by the sum of true positives and false positives. So it's going to look at the positive class only, which is the row. And the third metric is recall, which is similar because it also has the true positives on top there. But it's divided by the column now, true positives plus false negatives. Okay. So here you would get 7, which is the true positive, plus 7, because it's true positive again, plus 1, which is my false negative. So it's 7 over 8, which gives you 0.87%. And the way you interpret this is the proportion of actual spam emails that were correctly identified. So it's slightly different, right? And here we're going to report recall when we care more about false negatives than false positives. So these metrics really depend on how much one type of error costs over the other. And if you want a good balance between the two, you can use F1 score, which is this harmonic mean of precision and recall. So the formula is 2 times precision times recall divided by precision plus recall. Okay? So here the value would be 0.82. Right? So you see how these metrics are different. They give you different values, and they have different interpretations. And depending on how you want to evaluate your model, you would pick one over the other. Or it's also common to report all of them. Some people report all of them and compare, and then when you're, for example, writing a paper, you just discuss what happens in each scenario and how that could affect your model in real life, for instance. You don't have to pick one, right? You can pick 2 or 3 or all of them if that helps you evaluating your model, okay? Especially if they're considerably different, right? Then you might actually, that might be an interesting thing to explore in your results, saying, okay, well, actually my model is good for this, but it's bad for that, right? So if it's all good, then you can say, oh, my data set is balanced. Sometimes, if it's all good, you just report accuracy because it's already a good interpretable metric that everyone understands, and it's already strong enough. F1 score, again, is a metric that is not as interpretable as the others. All these metrics can be interpreted as percentages, but you see that you easily get confused of what these metrics are doing, right? So if you want, you can always calculate all of them, and then you see if they are different, and you can analyze your model, okay? Okay, finally, we can generalize these metrics for multi-class. You don't have to be limited for binary classification problems. You can compute accuracy, precision, recall, and F1 scores in multi-label classification or multi-class classification problems. And here's an example. Just talking about accuracy here, you would just sum your diagonal and divide by the total number of examples. And the other ones are, you take the average of precision 1, precision 2, precision 3, and then you have the final precision. For recall, you also take the average of the precision of the 3 classes, or the recall of the 3 classes the same, and here we report the F1 score, which is the same. Okay? All right, so that's all I had for today. Next lecture, which is next week, we're going to talk about how to deal with overfitting and also some ideas of how to improve the performance of our models. All right, thank you very much, and if I have questions, please let me know.